Welcome back to Element 4T Presents. My name's Andy, and in today's video, I'm going to show you how to turn this portable CRT television into a retro-style video arcade. And we're going to do it without modifying the TV at all. Now, you might be wondering how that's even possible, considering that there's no video inputs on this whatsoever. Basically just an antenna and a earphone jack. So if you're curious, stay tuned and I'll show you how it's done. This is the Sony Watchman model FD10A from 1987, not to be confused with the Sony Walkman, which was a portable cassette player also available at that time. It's powered by 4 AA batteries and it has a 2-inch black and white screen. And this has a really interesting design in that the tube is vertical in here. Originally I thought they were using a mirror at the top, but after looking more closely, what they've actually done is they've flattened out the tube, and what you're looking at is the inside of the back of the tube, and I just think that's a really clever design. All right, let's talk about our project. We're going to break this down into 2 parts, and in the first part, we're going to make a playable game prototype using the TV as a display. Then in a subsequent video, we'll add more features and polish, sound and battery and things like that, and of course an enclosure to make it look like a real arcade cabinet. So where do we start? Well, it's important to realize that this TV was made for one purpose, and that's to watch analog TV broadcasts. And at least in the United States, that hasn't been a thing since around the late 2000s. So in its current form, this is kinda useless unless you have your own TV transmitter. And that's exactly what we're gonna make. We're gonna make an RF modulator, which is basically a small, low-powered transmitter. So we have our TV, we have an RF modulator sending a signal to the TV. Then we're going to introduce some modern tech in the form of a Raspberry Pi Pico 2. We'll code our game on the Pico and generate an NTSC composite signal to feed into the RF modulator. Now the Pico, of course, doesn't have composite output, so we'll have to generate the signal from scratch as well, which should be fun. For input, I figure we use a game controller like an NES gamepad or an Atari joystick or something. We'll make custom controls for our cabinet in the next video, but for now, we'll just go with whatever I have that's easiest to program. The first challenge we're going to tackle is composite video generation. And as I mentioned, we're going to run our game on the Raspberry Pi Pico 2, but there's no video generation, or there's no video output on this microcontroller. Now, I'm not the first person to think of generating video with a Pico. In fact, there's a number of GitHub projects that allow you to do just that. However, I had problems with all of them. Now, that's not to say there's anything wrong with those projects, just that I couldn't get them to work. The first issue I ran into is that they all seem to use the PAL standard. PAL was used by most European countries, but I live in the US, which uses NTSC. So I tried modifying a couple of different projects to use NTSC timings, but that didn't work. Also, I prefer to use the Arduino core for the Pico, and I did actually get one of these projects to work with the Arduino IDE, but it did not result in a usable video signal. Rather than spend more time trying to get these to work, I decided to build my own solution from scratch. There is one thing I did borrow from a project called Pico Composite or P-Composite, and that's this resistor ladder. A resistor ladder acts as a simple digital to analog converter, or DAC. Composite video is 1 volt peak to peak, and with 5 bits of output, we can generate 32 distinct values within that range. The way this works is we take the value that we want to output, convert it to binary, and set 5 GPIO pins according to the bits in our binary number. Now, a pin is set high for a 1 and low for a 0. Then our resistor ladder converts those outputs to a voltage between 0 and 1 volts. In doing this, we can generate all kinds of waves and signals, including a composite video signal. So as an example, let's generate a sawtooth wave. A sawtooth wave goes up like a ramp and then drops straight down and starts over. So you can see what this is called a sawtooth wave. This can be approximated with a simple loop where we count from 0 to 31 and then repeat. In our loop, we have a function that enumerates over the pins and writes the individual bit values. And between outputting values, we have a 10 millisecond delay. 10 milliseconds times 32 values is 320, which is about a third of a second, which means we get 3 cycles per second or a 3 hertz wave. Let's hook this up to the oscilloscope. And as you can see, we have a sawtooth wave of approximately 3 hertz. Very nice. I want to make an old-style game like Asteroids or Space Invaders for this black and white TV, and I don't really need 5 bits of resolution for that. I really only need one level for sync, one for black, and one for white. Now, if I use 2 bits, I get 4 values, which is sync, black, white, and then an extra one can be used for gray, which is great, and that simplifies the circuit a lot. Now, this is all the hardware we need to generate a video signal. But first, we need to understand how NTSC works. NTSC is a color TV standard, but again, we're only dealing with black and white, so that makes our lives a lot easier. A CRT is a vacuum tube. A beam of electrons fire from the back of the TV to the front through this tube and sweep across the screen drawing lines left to right and top to bottom. This is how a field is drawn. 2 consecutive fields make up a single frame of video. One field has the even lines of the frame and the other has the odd lines, and those are displayed a 1/60th of a second apart. Our eyes merge those together into what appears to be a single solid frame. Now, the reason it's done this way is because broadcast TV signals have limited bandwidth, and by showing one field at a time, you cut that bandwidth in half. Even fields start with a half line, and odd fields start with a full line, but we're going to cheat and generate every field with only full lines because it's simpler. This is a trick that a lot of early computers and video game systems used. I made some comments in my code about the video signal timings. A full frame of interlaced video is 525 lines, but remember, we're treating a single field as a frame. So if you divide that by 2, you get 262.5, which we round up to 263. And that consists of 3 lines of equalization pulses, 3 lines of VSync, 3 more lines of equalization pulses, 14 blank lines, and 240 lines of active video. Only 240 lines are visible, and that could be even fewer due to something called overscan. Let's look at the signal for a line of active video. We've got the sync pulse at 0 volts, the back porch, which is approximately 1/3 of a volt, then the video information itself, and finally the front porch. Each part of the signal lasts for a specific amount of time, and the entire horizontal line has a duration of 63.5 microseconds. Now, we want to encode this analog signal data into digital form, so we quantize it. Believe it or not, NTSC video doesn't have an inherent horizontal resolution, so we have to pick one. I went with 256 pixels because it's a power of 2, so that means our resolution is 256 by 240. And because we know that the active video portion of a scan line takes 52.6 microseconds, we can work out exactly how many bytes we need to store everything. The idea is to generate the signals for these different line types in sequence, so equalization pulses, VSync, and so on. And then we're going to use the programmable I/O on the Pico to output those values on the GPIO pins, and that will produce our video signal. So here's the data for an active line of video. It starts with a horizontal sync pulse, which is 4.7 microseconds or 23 bytes. And that's exactly how many zeros we have here. 0 represents the sync level. And then we've got 4.7 microseconds of back porch, and then our video data. 1 is black, 2 is gray, and 3 is white, so we're generating a test pattern here. If we plug the composite cable into a TV and run the project, you can see what the pattern looks like. Can you believe this is just a microcontroller, a couple of wires, and a few lines of code? But I've only shown you the arrays with the video signal data. I haven't shown you how to take that data and output it with the extreme precise timing that we need. If you try to do that with digital write calls, it's not going to work. The CPU isn't designed for that, and there's also special dedicated I/O hardware called PIO. The PIO has state machines and instructions for processing I/O efficiently. So I had to dig into the SDK documentation to understand how to program the PIO, and honestly, there's just way too much information here for me to cover in this video. So definitely check out the official PDF if you want to program it yourself, but I will show you the PIO program that I wrote. It has one instruction, out. The destination is pins, and the bit count is 8. So that shifts 8 bits out of the output shift register to the GPIO pins. And it just does that over and over at a rate defined by the specified frequency. The out instruction is not a CPU instruction, and the PIO program requires a special compiler. So you can hunt that down in your SDK installation if you want. It's called PIO ASM, but I found a really handy online version that works just as well. And you can just take the output that generates and include it in your project. We need to make our video data, which is stored in a display buffer, available to the PIO, and we do that by setting up a DMA channel. DMA is direct memory access, and it's also independent of the CPU, so it allows us to copy a block of memory very quickly. And we also need to set up an interrupt that tells us when the DMA transfer is complete. So everything we're doing to generate our video is working pretty much behind the scenes, and the processor barely has to do anything. And that's great because the CPU, that CPU power is now available to draw things and run our game logic. One technique we're using for our game is double buffering. We actually have 2 full frames of video in memory at once. So while buffer 1 is being drawn, buffer 2 is displayed, and then we flip buffers, so while buffer 2 is being drawn, buffer 1 is displayed. This is a process that needs to be synchronized. So you can see in the DMA handler that we check if we're ready to flip buffers. And that just means that our game has fully prepared a frame for rendering, and we can now swap our buffers. Otherwise, frames get skipped, which is bad. In our main program loop, we wait for that flag to be false, so we're not drawing frames faster than they can be displayed, which is also bad. Now we have a composite video signal with nowhere to put it. I could modify this old TV to accept a composite video signal, but some people don't like destructively modifying old hardware, especially when it's in good working condition, and they're not making these things anymore, so I get it. What we want is an RF modulator, similar to the one in this Atari 2600 game console. You can buy them online, and in fact you can even buy RF modulator chips, but we're going to build one from scratch because it's more fun. I found some plans on how to build one in an old magazine article. This is from the January 1985 issue of Elector magazine. This article would have been available when the Watchman was on store shelves, and it describes how to build a VHF-UHF TV modulator. Let's just quickly read what it says at the top here. Computers, video games, video cameras, games computers, all of these produce video signals that must be displayed via television set. If the TV receiver in question does not have a video input and its owner is reluctant to vandalize it in order to fit one, then this sort of modulator is the obvious solution. It's a simple circuit that processes video signals to enable them to be fed straight into the TV set's aerial input. So this is exactly what we're looking for. Here we have a schematic and a parts list and a picture of a single-sided PCB. And down here we have this note. Fortunately, the printed circuit board for the modulator is only single-sided. The large copper surface acts as the ground plane. Now, the article hints that you can buy the board from Elector, but that was in 1985, so I'm going to go ahead and build mine with protoboard. Now, the problem, of course, is that most protoboards don't have a ground plane, but they do exist, and I went ahead and bought one. This looks like a regular protoboard on one side, and if you look closely on the back, you can see conductive metal between the holes that you can use as a ground. I can already tell this is going to require really careful soldering to avoid any bridging. Most of these parts are common and easy to find, resistors and capacitors. Apparently the Schottky diodes were tricky to find back in the day, but I had no trouble getting them. We don't need the 7805 voltage regulator, so we can skip that. The BFR91 is an NPN transistor specifically for use in RF amplifiers, and it's obsolete. If you know of a suitable replacement, leave a note in the comments or on the Element 14 community website. The inductors are where things get a little weird. They want you to wrap wire around a ferrite bead, which we're going to do, and then they say this: the fourth inductor L3 can simply be bought, and the only specification is that it has 1 microhenry inductance. Do a search for 1 microhenry inductors and you're going to get a ton of results that all look completely different, and I personally don't know anything about inductors. This led me down an AI rabbit hole involving Q values and SRFs and a whole bunch of other stuff, because apparently you can't just buy any old inductor and expect it to work in your high frequency RF project. So I gave it my best shot, and hopefully these will do the job. Here are all the components we need, and now we need to figure out how to arrange them on the board. This old magazine scan is hard to read, so I opened it up in paint.net and drew different layers on top so I could reason about how things are supposed to be connected. And then it's a matter of dropping components in and trying to make them fit. So I discovered that I don't personally have the skills to solder and film this at the same time. I tried a couple times and it didn't work out. So let me show you the final board, and I'll walk you through exactly what I did. The first thing you'll notice is that I've added a few things that aren't in the picture. We have this RF output cable, then this is the composite input, and then this is just a USB breakout board I had lying around that we'll use for power. These are our 2 Schottky diodes, and those are polarized, so the direction's important. Our 27 megahertz oscillator, and the 1 microhenry inductor. P1 and P2 are potentiometers, which I've already adjusted. Then we've got our little hand-wound inductors, and another thicker air-wound inductor. And of course the BFR91 high-frequency transistor, which performs the amplitude modulation. Why don't we plug this into the TV and see if we can get it to display a picture? Okay, I cheated a little and skipped ahead. This is actually the title screen to a game I made on the Pico. Let's take a look at how it was made. Cosmic Attack is a Space Invaders-like game with my own original code and graphics. They didn't have Photoshop to create game art in the late 70s, but they did have graph paper, and you can see an example of this in this old Commodore 64 user manual, where they show how to make a sprite. I drew all the in-game graphics this way, which is actually kind of fun, and then I manually typed the pixel values out as byte arrays. 0 is transparent, 1 is black, 2 is gray, and 3 is white. But unlike the C64, the Pico doesn't have dedicated sprite hardware. I had to write graphics routines like draw sprite and draw text to do this in software. The title screen was too large to do on paper, so I wrote a simple C# utility program to convert a PNG image to a CPP file. I included that file in the project, and I wrote a draw screen function to draw an entire screen of data at once. When the game runs, the update and draw functions are called every frame. I used arrays of function pointers to call different logic depending on what state the game's in. So for example, if you're on the title screen, a different function executes than if you're on the game over screen. All the game logic's currently stored in one file, but that might change as more features are added. For input, I decided to go with Atari's CX78 Plus gamepad because it was so easy to wire up and program. I just took a cable with a male DB9 connector on one end and soldered some jumper wires to the other end. I only needed 4 wires, 3 for inputs and 1 for ground, because the game only uses the left and right directions and 1 fire button. Input state is updated every frame, and I have separate variables to track whether a button was pressed on the current frame. And here it is in action. We now have a functioning game system prototype built on little more than a Raspberry Pi Pico and some wires. It's amazing what such a small, inexpensive board can do. But there's one last thing we have to do, and that's to see if we can get the image to display on the Sony Watchman, which is the whole point of this project. We'll scan the channels and see if we can see anything. And there it is. You'll notice that this doesn't actually have to be plugged into anything. This really is broadcasting wirelessly over a small distance. I wasn't able to finish all the game features in time. For instance, the aliens don't shoot and the shields don't do anything yet. But I'll continue working on it after this video is released, and in an upcoming video, we'll add sound and design an enclosure to make it look more finished. That's all we have for today. Have you ever used old technology to build something new? Let us know in the Element 14 community at the link in the description, and we'll see you next time.